July 11, 1942, Akutan Island, Alaska. Lieutenant Commander Eddie Sanders of the United States Navy Technical Air Intelligence Center stood in the rain-soaked tundra, staring at what should have been impossible. Before him lay an intact Mitsubishi A-6M-20 fighter, the aircraft that had terrorized Allied pilots across the Pacific for 8 months. The plane that American intelligence had deemed nearly mythical in its capabilities. Sanders knelt beside the fuselage, running his hand along the skin panels. They felt impossibly thin, almost fragile. He tapped the surface with his knuckles. The sound was hollow, metallic, but somehow wrong. Too light, too delicate. This was the fighter that had achieved kill ratios of 12-1 against American aircraft? This flimsy construction had dominated the skies from Pearl Harbor to the Coral Sea. His engineering team began their preliminary examination, and within minutes, the first shocking discovery emerged. The skin thickness measured just 0.031 inches, less than 1 millimeter, thinner than a dime. Captain William Taylor, a structural engineer from Wright Field, actually laughed in disbelief. "This isn't armor," he said. "This is barely enough metal to hold fuel. How does this thing survive combat?" But the real shock came when they began removing panels to examine internal structures. The entire aircraft was built to weight tolerances that violated every principle of American aircraft design. Where American fighters used redundant structures, backup systems, and protective armor, the Zero used the absolute minimum material necessary to achieve flight. It was an engineering philosophy that seemed suicidal, yet had proven devastatingly effective. What the American team discovered over the next 6 weeks would revolutionize their understanding of aircraft design, reveal the desperate material shortages driving Japanese engineering, and ultimately provide the tactical intelligence that would turn the air war in the Pacific. The captured Zero would be tested, measured, analyzed, and flown until every secret was extracted, and those secrets would kill thousands of Japanese pilots who flew aircraft designed for a war Japan could no longer fight. The story of the Akutan Zero began 6 weeks earlier. On June 4, 1942, during the Battle of Midway, Petty Officer First Class Tadayoshi Koga, a talented young pilot from the aircraft carrier Ryujo, participated in the diversionary attack on Dutch Harbor, Alaska. His Zero, part of a 12-plane strike force, strafed American positions with typical Japanese precision. But during the attack, Koga's Zero took a single bullet through the return oil line, a minor hit barely worth noting in combat. The kind of damage American aircraft routinely survived and returned home from. For the Zero, it was a death sentence. Without oil pressure, Koga's engine would seize within 30 minutes. He radioed his flight leader, requesting permission for emergency landing. The nearest Japanese base was too far. He would have to land on Akutan Island, 30 miles east of Dutch Harbor, and await rescue. Standard procedure. Japanese forces controlled the area. Recovery teams would retrieve him within days. Koga selected what appeared to be a smooth, grassy field on Akutan's northern coast. He lowered his landing gear, lined up his approach, and committed to landing. What he perceived as solid ground was actually muskeg, a thick layer of wet peat moss covering swampy soil. The moment his wheels touched, they sank. The Zero flipped forward violently. Koga, not wearing his shoulder harness per Japanese pilot custom to improve visibility, was thrown forward into the instrument panel. His neck snapped instantly. The Zero, inverted, settled into the muskeg. The soft ground cushioned the impact, preventing structural damage. The aircraft lay there undiscovered for 5 weeks. Rain and fog concealed it from American search aircraft. Japanese rescue teams, driven away by American naval presence, never returned. On July 10th, a U.S. Navy patrol vessel spotted wreckage on Akutan. The next day, Sanders and his team arrived. What they found was a miracle of intelligence opportunity. The Zero was 95% intact. The engine was undamaged. The guns were loaded. The instruments were functional. Even the manufacturer's technical documents were still in the cockpit map case. It was as if someone had gift-wrapped Japan's most closely guarded aviation secret and left it for American engineers to find. The recovery operation began immediately. The Akutan site was remote, accessible only by sea or air, and weather permitted work just a few hours daily, but the intelligence value justified any effort. The Zero was carefully excavated from the muskeg, disassembled into transportable sections, and shipped to San Diego. By August 15th, it was at the Naval Air Station North Island facility, ready for comprehensive analysis. The technical examination revealed construction methods that shocked American engineers. The Zero's primary structure used extra super duralumin, a Japanese aluminum alloy designated 7575. This alloy, developed specifically for aircraft, offered high strength at extremely low weight, but the application philosophy differed radically from American practice. Where American engineers designed with safety factors of 4-1 or 5-1, Japanese engineers used factors of of 1.5 to 1 or even 1.2 to 1. Every component was built to the absolute minimum strength required for its function. Nothing extra, no redundancy, no safety margin. The result was an aircraft weighing 5,174 pounds loaded, compared to the American F-4F Wildcat at 7,975 pounds. The Zero was 35% lighter while carrying similar fuel and armament. This weight advantage translated directly into performance. Rate of climb, turn radius, range. Everything improved when you removed 1,200 pounds of structure, armor, and safety equipment. The detailed structural analysis continued for weeks. Engineers measured every panel thickness, every spar dimension, every rivet pattern. They discovered construction techniques that simultaneously impressed and horrified them. The wing spars, for instance, used a unique combination of aluminum extrusions and laminated structures that achieved remarkable strength at minimal weight. American metallurgists studied the spar construction for days, trying to understand how such delicate-appearing structures could withstand combat loads. The answer was precision manufacturing beyond what American industry routinely achieved. Japanese craftsmen filed, fitted, and adjusted each component to tolerances measured in hundredths of millimeters. The labor intensity was staggering. Each Zero required approximately 25,000 man-hours to construct, compared to 15,000 for an American fighter. This explained why Japanese production never exceeded American output despite desperate need. They couldn't mass-produce aircraft built like Swiss watches. The fuel system analysis revealed both brilliance and catastrophic vulnerability. The Zero carried 518 liters of fuel in multiple tanks distributed throughout the fuselage and wings. For comparison, the F-4F Wildcat carried 663 liters, but weighed 55% more. The Zero achieved its legendary range, over 1,900 kilometers, through extreme fuel efficiency enabled by lightweight. But the fuel tanks had no self-sealing protection. In American aircraft, fuel tanks were surrounded by rubber layers that automatically sealed bullet holes. This system added weight, but prevented fuel fires from minor hits. The Zero's designers, obsessed with weight reduction, eliminated this protection. The result was an aircraft that burned catastrophically when hit in the fuel system. American pilots had reported this vulnerability, describing Zeros exploding into fireballs from single incendiary rounds. The engineering analysis confirmed these reports and explained them. Without self-sealing tanks, a single bullet could drain fuel or ignite vapors. The armor analysis was even more shocking. The Zero had none. Zero armor protection for the pilot. Zero armor around the engine. Zero armor protecting fuel tanks. The pilot sat exposed, protected only by the thin aluminum fuselage skin and his parachute pack. American pilots wore flak jackets and sat behind 3/8-inch steel plates. They flew aircraft with armored windscreens and engine shields. The Zero's pilot had a sheet metal seat and hope. Captain James Flatley, a Wildcat ace who would later test fly the captured Zero, examined the cockpit with disbelief. "I couldn't believe any Air Force would send pilots into combat in this," he said. "We lost good men to this airplane, and now I see the pilots who flew it had no protection at all. They were as vulnerable as we were, more so. It was mutual suicide." The weight savings from eliminating armor totaled approximately 350 pounds. That weight became performance. The Zero could outclimb, outturn, and outrange American fighters because Japanese designers chose performance over protection. It was a calculated trade-off based on Japanese tactical doctrine emphasizing offensive aggression and skilled piloting over defensive survivability. The armament analysis revealed similar compromises. The Zero carried two 7.7mm machine guns in the nose with 500 rounds each, and two 20mm cannons in the wings with 60 rounds each. The cannons were powerful but suffered from low ammunition capacity and slow rate of fire. Japanese pilots practiced ammunition conservation obsessively. American pilots, by contrast, flew aircraft with 2,000 to 3,000 rounds of 50 caliber ammunition. They could fire sustained bursts. Zero pilots had to count rounds and make every shot count. The engine examination provided crucial tactical intelligence. The Nakajima Sakai 1-2 engine, a 14-cylinder radial producing 940 horsepower, was sophisticated and well-engineered. But it had a critical limitation. The engine's supercharger delivered maximum power only below 15,000 feet. Above that altitude, power dropped significantly. American engines, particularly the Pratt and Whitney R2800 and later Corsairs and Hellcats, maintained power to much higher altitudes. This meant the Zero dominated low-altitude combat but lost advantage above 20,000 feet. American pilots who had survived encounters reported this phenomenon. The Zero seemed unbeatable below 10,000 feet but struggled at high altitude. The engineering analysis confirmed these observations observations and quantified them. The hydraulic system, or rather the lack of one, surprised American engineers. The Zero used no hydraulic power. Landing gear operation was manual, requiring the pilot to hand crank the gear up or down, a process requiring 20 cranks per side. Flaps were electrically operated. Gun charging was manual. By contrast, American fighters used hydraulic systems for landing gear, flaps, and various controls. The hydraulic systems added weight and complexity but reduced pilot workload. The Zero's designers chose simplicity and lightweight over pilot convenience. This philosophy pervaded every system. The electrical system was minimal. The radio was simple and short-ranged. The instruments were basic. Everything that didn't directly contribute to flight performance or offensive capability was minimized or eliminated. The philosophy was clear: build the lightest possible airframe, install the minimum necessary equipment, and rely on pilot skill to compensate for lack of systems. The test flight program began in September 1942. The Zero had been reassembled, inspected, and cleared for flight. The honor of first flight went to Lieutenant Commander Eddie Sanders, who had led the recovery team. His first takeoff revealed the Zero's most famous characteristic immediately: it climbed like a rocket. Sanders later reported that the Zero's rate of climb at sea level exceeded 4,000 feet per minute, far superior to any American fighter then operational. The climb performance was breathtaking and terrifying. American fighters took 5 to 7 minutes to reach 20,000 feet. The Zero could reach that altitude in less than 4 minutes. The turning performance was equally impressive. Sanders performed a series of turning tests against a camera-equipped aircraft at various altitudes. The results confirmed every combat report. The Zero could outturn any American fighter then in service. At 200 knots indicated airspeed and 10,000 feet altitude, the Zero sustained a turn radius of approximately 700 feet. The F-4F Wildcat required over 1,000 feet. The difference was literally life or death in dogfighting. But the test program also revealed critical weaknesses. The Zero's controls became extremely heavy at high speeds. Above 300 knots, the ailerons required so much force that combat maneuvering became nearly impossible. American fighters with hydraulically boosted or carefully balanced controls maintained maneuverability at high speed. The Zero's manual flight controls, perfect for low-speed dogfighting, became a liability in high-speed engagements. The dive performance was even more compromised. The Zero's light structure couldn't handle high G pullouts from steep dives. Sanders tested the dive limits carefully. Never exceeding 400 knots indicated airspeed. At those speeds, the controls felt mushy and unresponsive. One test pilot reported feeling the wings flexing visibly during a high-speed pullout, a terrifying sensation that prevented him from pushing the aircraft to structural limits. American fighters, built heavier and stronger, could dive at speeds exceeding 450 knots and pull hard at the bottom. This became a crucial tactical advantage. If an American pilot found himself in a losing engagement, he could dive away. The Zero couldn't follow without risking structural failure. The endurance tests revealed another uncomfortable truth about Zero operations. To achieve their legendary range, Japanese pilots flew at extremely lean fuel mixtures and low power settings. Combat power could be sustained for only 10 to 15 minutes before fuel exhaustion became critical. American pilots, with larger fuel reserves and less concern about conservation, could maintain combat power much longer. This explained reports of Zeros breaking off, apparently winning engagements. They weren't retreating. They were running out of fuel. Now, if you're finding these technical revelations fascinating, consider subscribing to our channel. We bring you the untold stories of World War II's greatest intelligence coups and the engineering secrets that changed the course of history. Hit that subscribe button and notification bell so you never miss these incredible accounts of how American ingenuity turned enemy technology into victory. The tactical analysis based on test flights produced detailed recommendations for combat pilots. These recommendations, distributed throughout the Pacific Fleet in October 1942, would fundamentally change how American pilots fought. First recommendation: never dogfight a Zero below 200 knots or 15,000 feet. The Zero's turn performance and climb rate at low speeds and altitudes made close-in maneuvering suicidal. American pilots who followed their instincts and tried to turn with Zeros died. Second recommendation: use altitude and speed. Engage from above 20,000 feet if possible. Dive through the fight, fire a burst, and climb away using superior speed. Never slow down to turn with the enemy. Third recommendation: if engaged, dive away. The Zero cannot follow high-speed dives without structural risk. American aircraft can outdive and outrun the Zero in any vertical maneuver. Fourth recommendation: use teamwork. The Zero excels in single combat but struggles against coordinated attacks. Two American fighters working together can overwhelm one Zero by attacking from multiple angles simultaneously. simultaneously. Fifth recommendation: aim for the fuel tanks and engine. The Zero has no armor and no self-sealing tanks. Any hit to these areas will likely cause catastrophic fire. These tactics, developed directly from analysis of the captured Zero, became known as the Thatch Weave, after Commander John Thack, who formalized the defensive formation. But the tactics were enabled by hard technical data from the Akutan Zero. Pilots who followed these recommendations survived. Those who ignored them and tried to dogfight died. The kill ratios shifted dramatically. In the first 6 months of 1942, Japanese pilots achieved approximately 12 kills for every loss in fighter-versus-fighter combat. By mid-1943, after the tactical recommendations spread throughout American forces, the ratio had reversed. American pilots were achieving 3 to 4 kills for every loss. The shift wasn't due to better aircraft. The F-4F Wildcat that bore the brunt of combat through 1943 was still inferior to the Zero in most performance parameters. The shift came from understanding the Zero's limitations and exploiting them systematically. The Akutan Zero's intelligence value extended beyond tactical recommendations. American aircraft designers used the detailed technical analysis to guide next-generation fighter development. The F-6F Hellcat, which entered service in early 1943, incorporated lessons learned from the captured Zero. The Hellcat couldn't outturn the Zero, but it didn't try. Instead, it focused on speed, high-altitude performance, ruggedness, and firepower. The Hellcat could dive faster, climb at high altitude better, survive battle damage, and deliver more firepower than the Zero. It was designed to fight the Zero using American strengths rather than matching Japanese capabilities. The result was an aircraft with a 19-to-1 kill ratio against Japanese fighters, the best of any American fighter in World War II. The F-4U Corsair, also entering service in 1943, followed similar philosophy. Fast, powerful, heavily armed, and nearly invulnerable compared to Japanese fighters, the Corsair could engage and disengage at will, fighting only when conditions favored American advantages. Japanese pilots flying Zeros found themselves hunted by aircraft they couldn't catch, couldn't damage, and couldn't outgun. The technical intelligence from one captured aircraft had spawned an entire generation of purpose-built Zero killers. The Japanese response to the captured Zero was surprisingly slow. American forces made no secret of testing captured enemy equipment. Photographs of the Akutan Zero in American markings appeared in intelligence briefings and training materials. Japanese intelligence certainly knew Americans possessed an intact Zero by late 1942. Yet Japanese aircraft development continued along existing paths. The A6M30, introduced in 1943, added minimal improvements. Engine power increased slightly. Some structural reinforcement was added. But the fundamental design philosophy remained unchanged. Lightweight, maximum maneuverability, minimal protection. The Japanese Navy considered developing a replacement for the Zero, but couldn't agree on requirements. Some officers wanted a heavily armed interceptor. Others demanded retention of the Zero's maneuverability. Resource constraints prevented developing multiple aircraft types simultaneously. The result was paralysis and incremental improvements to an increasingly obsolescent design. By 1944, the Zero faced American fighters that outclassed it in every parameter except turning radius, and American pilots had learned not to turn. The Zero's construction methods also revealed Japan's critical material shortages. The aluminum alloy used in the Zero, while sophisticated, required materials Japan increasingly couldn't obtain. Imports of bauxite, the aluminum ore, were being interdicted by American submarines. Japanese aluminum production peaked in 1943 and declined thereafter. Engineers examined the Akutan Zero's alloy composition and identified critical materials. Copper, magnesium, and manganese were essential to the 7575 alloy's properties. All three materials were increasingly scarce in Japan. American intelligence analysts predicted, correctly, that Japanese aircraft quality would decline as material shortages forced substitution of inferior alloys. By late 1944, Japanese aircraft were being constructed with lower quality aluminum containing more impurities. Structural strength decreased. Fatigue life shortened. Aircraft began failing from structural fatigue rather than combat damage. The Akutan Zero had revealed not just tactical vulnerabilities, but strategic industrial weaknesses. The pilot training implications were equally significant. The Zero's lack of forgiving characteristics meant it required skilled pilots to fly effectively. American test pilots noted that the Zero demanded constant attention, careful management of speed and altitude, and precise control inputs. It was not a forgiving aircraft for novice pilots. This aligned with Japanese training philosophy in early war. Japanese naval aviators underwent years of intensive training, accumulating hundreds of flight hours before combat assignments. assignment. They had the skill to exploit the Zero's capabilities and manage its limitations. But by mid-1943, Japan was losing trained pilots faster than they could be replaced. New pilots received abbreviated training, sometimes less than 100 flight hours before combat deployment. These inadequately trained pilots, flying unforgiving aircraft against well-trained Americans in superior machines, died in shocking numbers. The captured Zero helped American intelligence predict this training crisis. If the Zero required high skill to fly effectively, and Japan was losing skilled pilots, then Japanese fighter effectiveness would collapse as pilot quality declined. This prediction proved devastatingly accurate. By 1944, American pilots reported encountering Japanese pilots who barely knew how to fly, much less fight. The maintenance requirements revealed through examination of the Akuten Zero provided another intelligence windfall. The aircraft's precision construction required skilled maintenance. Tolerances were tight. Adjustments were complex. Many components required hand-fitting. The maintenance manual, recovered from the cockpit, was hundreds of pages long with detailed procedures for tasks American aircraft accomplished with simple bolt-on replacement. This maintenance intensity became a critical vulnerability as the war progressed. Japanese forward bases lacked trained technicians and proper facilities. Aircraft sat broken, awaiting parts or expertise that never arrived. Serviceability rates plummeted. At peak efficiency, Japanese carrier air groups maintained 70 to 80% aircraft availability. By 1944, availability often fell below 40%. American forces, with simpler aircraft and better logistics, maintained 60 to 70% availability even under primitive conditions. The Akuten Zero had exposed Japan's industrial weaknesses, training limitations, and logistical vulnerabilities. One captured aircraft provided intelligence that shaped American tactics, influenced fighter design, and predicted Japanese decline. The propaganda value of the captured Zero was carefully managed. The U.S. military released limited information publicly to avoid revealing the extent of intelligence gained. But within military circles, the Akuten Zero became legendary. Pilots who had feared the Zero learned it was mortal. Engineers who had assumed Japanese technological superiority discovered it was achieved through extreme trade-offs rather than breakthroughs. Intelligence analysts who had considered Japanese industry mysterious found it was actually fragile and resource-constrained. The psychological impact on American forces was significant. The Zero, from terrifying mystery to understood opponent, no longer dominated American thinking. Pilots approached combat with confidence based on knowledge rather than fear based on reputation. The statistical evidence of this shift was clear. In June 1942, immediately after Midway but before tactical recommendations from the Akuten Zero spread, American fighter pilots in the F-4F Wildcat faced approximately even odds against Zeros. Loss ratios were roughly 1-to-1 in pure fighter combat. By June 1943, after Thatch-Weave tactics and Zero analysis were widely distributed, loss ratios had shifted to approximately 3 American kills for every loss. By June 1944, with new American fighters designed to exploit Zero weaknesses operational, ratios exceeded 10-to-1 in many engagements. The change wasn't gradual. It was a sharp transition from parity to dominance, and the Akuten Zero marked the inflection point. The captured aircraft allowed American forces to transition from defensive survival to offensive dominance in the air war. Japanese pilot accounts from late war confirm American tactical adaptations. Lieutenant Saburo Sakai, Japan's highest-scoring surviving ace, wrote in his memoir about the frustration of facing American pilots who refused to fight on Japanese terms. They would not dogfight, he noted. They stayed high and fast. When they attacked from advantage and disengaged before we could respond. It was as if they knew exactly what our aircraft could and could not do. They did know. They knew because American engineers had measured, tested, and analyzed every capability and limitation of the Zero. They had quantified what had been reported anecdotally. They had discovered weaknesses Japanese pilots themselves might not have fully appreciated. The intelligence was comprehensive, accurate, and actionable. The Akuten Zero was eventually transferred to the Smithsonian Institution in 1961, where it remained in storage until restoration began in the 1990s. Today, it's displayed at the Smithsonian's National Air and Space Museum as a testament to its historical significance. But its real legacy isn't in museums. It's in the thousands of American pilots who survived because they knew how to fight the Zero. It's in the design of the Hellcat and Corsair, aircraft that dominated the Pacific Air War. It's in the understanding that intelligence, properly gathered and applied, can be as decisive as industrial production or military courage. Before we continue to the final chapter of this intelligence triumph, I want to invite you to join join our growing community. If you're enjoying these deep dives into World War II's secret technical battles, please subscribe and hit that notification bell. We're committed to bringing you the stories that changed history, the intelligence coups and engineering victories that won the war. Your support helps us continue creating this content. Thank you, and let's continue. The broader impact of the Akutan Zero extended to American aircraft industry practices. Engineers at Grumman, Vought, Lockheed, and other manufacturers received detailed technical reports on Zero construction. They studied Japanese manufacturing techniques, materials, and design philosophy. Some techniques were adopted where they offered advantages without compromising safety. The use of laminated structures in wing spars, for instance, appeared in several American designs. But more importantly, American engineers learned what not to do. The Zero represented an extreme design philosophy that sacrificed too much for performance. American manufacturers maintained their commitment to pilot protection, structural safety margins, and system redundancy. They found ways to improve performance without compromising survivability. The result was fighters that were nearly as maneuverable as the Zero while being far more survivable. The P-38 Lightning, P-47 Thunderbolt, and P-51 Mustang in Europe followed similar philosophy. Performance through power and speed rather than lightweight. These aircraft couldn't turn with German or Japanese fighters, but they didn't need to. They could engage and disengage at will, fighting only when conditions favored them. The Akutan Zero's lessons applied across all theaters. The intelligence sharing between Allied forces ensured that lessons from the Pacific reached European theaters, and vice versa. British Commonwealth forces fighting in Burma and the Indian Ocean received detailed tactical recommendations based on Zero analysis. Soviet forces, though not directly engaged against Japanese aircraft in most of the war, received technical intelligence through Lend-Lease channels. The captured Zero became a teaching tool for the entire Allied air effort. Training programs incorporated Zero tactics and capabilities. New pilots learned not from painful experience, but from systematic study of a known opponent. The survival rate of newly deployed pilots improved measurably. In early 1942, approximately 40% of American pilots were lost during their first 5 combat missions. By mid-1943, this rate had dropped below 20%. Better training, improved tactics, and understanding of enemy capabilities contributed to this improvement. The Akutan Zero was a significant factor in that understanding. The Japanese attempt to recover or destroy the Akutan Zero came far too late. By the time Japanese intelligence confirmed the aircraft's capture in late 1942, it had been thoroughly analyzed. A commando raid to destroy it would have been pointless. The intelligence had already been extracted and distributed. Japanese naval staff considered the loss but couldn't quantify its impact. They knew Americans had captured a Zero. They didn't know, or perhaps didn't want to acknowledge, how completely that single aircraft would compromise their air superiority. The psychological denial was understandable. Accepting that one captured aircraft could shift the balance of air power required accepting that the Zero's advantages were fragile and easily countered once understood. The material analysis of the Akutan Zero also provided economic intelligence. American analysts calculated the material content of the Zero, quantified the manufacturing labor, and estimated Japanese production capacity. These calculations fed into strategic planning for the submarine campaign against Japanese shipping. If each Zero required X tons of aluminum and aluminum required Y tons of bauxite, then sinking bauxite shipments would degrade fighter production by Z aircraft per month. The strategic bombing campaign against Japanese industry later in the war also benefited from this analysis. Knowing which materials were critical allowed targeting of specific production facilities. Aluminum refineries received high priority. Magnesium production facilities were targeted. The supply chain analysis derived partly from studying the Akutan Zero guided strategic bombing priorities. The post-war examination of Japanese records confirmed the Akutan Zero's impact. Japanese naval aviation staff assessed that American tactical adaptations in mid-1943 directly resulted from technical intelligence on the Zero. Their own analysis concluded that loss of the Akutan aircraft provided Americans comprehensive understanding of Zero capabilities and limitations. Some Japanese officers argued the loss required immediate development of a replacement fighter. Others insisted the Zero's superiority in skilled hands remained valid. The debate continued while American industry produced fighters specifically designed to kill Zeros. By the time Japan committed to Zero replacement in late 1943, American next-generation fighters were already operational. The Japanese A-7M Reppu, intended as the Zero's successor, wouldn't see combat before war's end. Industrial capacity, resource shortages, and bombing disruption prevented its mass production. The Zero, designed in 1938, fought until 1945 against opponents designed specifically to defeat it. The tactical evolution of American fighter combat, from defensive survival to offensive dominance, can be traced through combat reports and loss statistics. Before the Akutan Zero capture, June 1942, American fighter losses versus Japanese fighters, approximately 1-to-1 ratio. After Akutan Zero analysis and tactical distribution, December 1942, ratio shifts to 1.5-to-1 in American favor. With new American fighters designed using Zero intelligence, June 1943, ratio reaches 3-to-1 American favor. Late war with overwhelming American advantages, June 1944, ratio exceeds 10-to-1 in most engagements. This progression from parity to dominance took just 24 months. The Akutan Zero marked the beginning of that transformation. The human element of this story shouldn't be forgotten. Petty Officer Tadayoshi Koga, whose fatal crash landing delivered the Zero to American hands, was a skilled pilot doing his duty. His death was accidental, caused by mechanical failure and difficult landing conditions. He had no way to know his misfortune would contribute to Japan's defeat. American recovery and intelligence personnel who recognized the Zero's value and extracted every possible insight from it performed exceptional service. They understood they held an intelligence treasure and exploited it fully. The test pilots who flew the Zero, knowing it could have structural weaknesses or sabotaged components, demonstrated courage. They risked their lives to gain tactical knowledge that would save thousands of others. The engineers who spent months analyzing every rivet and measuring every panel provided the detailed intelligence that made tactical recommendations credible. Their meticulous work transformed a captured aircraft into actionable intelligence. The modern legacy of the Akutan Zero extends beyond World War II history. It established principles of technical intelligence exploitation still used today. Capture enemy technology intact, analyze it comprehensively without preconceptions, share findings rapidly with operational forces, incorporate lessons into tactics, training, and future development. These principles guided American intelligence throughout the Cold War and remain relevant today. The Zero analysis also demonstrated the value of understanding enemy engineering philosophy. The Zero wasn't poorly designed. It was brilliantly designed for specific requirements within severe constraints. Understanding those constraints revealed vulnerabilities. Modern technical intelligence still seeks to understand not just what enemy systems can do, but why they were designed that way and what trade-offs were made. The Akutan Zero teaches that enemy capabilities, however impressive, always have limitations. Finding and exploiting those limitations requires systematic analysis and rigorous testing. Assumptions and preconceptions must be set aside. The evidence must guide conclusions. American intelligence approached the Zero without assuming American engineering philosophy was superior. They studied Japanese methods objectively, adopted useful techniques, and identified exploitable weaknesses. This intellectual honesty produced accurate, actionable intelligence. The story of the Akutan Zero is ultimately about the decisive advantage that knowledge provides in warfare. Two forces with similar equipment can achieve vastly different outcomes based on how well they understand their own capabilities and their enemy's limitations. The American forces that fought Zeros after October 1942 had the same F-4F Wildcats they'd flown since Pearl Harbor, but they had knowledge. They knew exactly what the Zero could and couldn't do. They knew how to fight it successfully. That knowledge, derived from 6 weeks of analysis of one captured aircraft, shifted the air war in the Pacific from desperate survival to confident dominance. The Zero, from mystery to understood opponent, lost its psychological advantage. Japanese pilots, from terrifying opponents to mortal enemies with quantified weaknesses, could be defeated systematically. The transformation took 1 year, from June 1942 to June 1943, and the Akutan Zero was the catalyst. When American pilots examined the captured Zero and discovered its construction, they couldn't believe an aircraft with such thin skin and minimal structure could have dominated the Pacific Air War. But they learned, systematically and completely, exactly how it had achieved that dominance and, more importantly, how to defeat it. The aluminum panels they thought might be wood were actually sophisticated alloy. The apparently fragile construction was precision engineering to extreme weight limits. The lack of armor wasn't oversight but calculated trade-off. Everything about the Zero made sense once understood, and once understood, it could be defeated. The captured Zero didn't win the war, but it enabled the pilots and aircraft that did. It provided knowledge, and knowledge, properly applied, proved more valuable than any number of aircraft or any advancement in technology. technology. The Akutan Zero stands as testament to the intelligence value of captured enemy equipment and the decisive advantage that comprehensive understanding provides in warfare. From a rain-soaked island in Alaska to the design tables of American aircraft, manufacturers from tactical training syllabi to combat victories across the Pacific, the influence of one captured fighter extended through every aspect of the air war. The Japanese never knew how completely that single aircraft, abandoned in Alaskan Muskeg, would compromise their aerial advantage. They never fully understood how American systematic analysis transformed mystery into mastery. They continued building Zeros while Americans built Zero killers. The result was inevitable. By war's end, the Zero, once the world's most feared fighter, had become a death trap for inadequately trained pilots facing opponents who knew every secret of its construction and every limit of its capability. The American pilots who first examined the captured Zero saw thin aluminum and minimal structure. They thought it might be wood. They couldn't believe something so apparently fragile had killed so many of their friends. But after comprehensive analysis, flight testing, and tactical exploitation, they understood. The Zero was a brilliantly engineered aircraft designed to maximize performance within severe material constraints. It achieved remarkable capabilities through extreme trade-offs, and those trade-offs, once understood, became vulnerabilities that American forces exploited ruthlessly. The transformation from feared opponent to understood vulnerability took 1 year and began with one crashed fighter on a remote Alaskan island. The intelligence coup of the Akutan Zero remains one of World War II's most consequential technical intelligence operations. One aircraft provided insights that influenced fighter design, shaped tactics, predicted strategic vulnerabilities, and ultimately contributed to American air superiority in the Pacific. The Zero's secrets, extracted from rain-soaked wreckage, proved more valuable than entire squadrons of aircraft. Knowledge defeated mystique, analysis defeated reputation, and systematic intelligence exploitation defeated what had seemed like unbeatable Japanese air superiority. The American pilots who examined the captured Zero learned that what seemed impossible, fragile aluminum defeating armored opponents, was actually engineered precision that could be understood, countered, and defeated. They learned not to fear the Zero but to respect it as a worthy opponent with quantified capabilities and exploitable limitations. And they learned that in warfare, understanding your enemy can be as decisive as any weapon. The Akutan Zero taught this lesson perfectly, and the thousands of American pilots who survived the Pacific Air War benefited from that lesson every day. They flew against the aircraft that had once seemed invincible but became, through knowledge, just another defeatable opponent.